Hello everyone. Have you ever wondered why light waves don't just vibrate chaotically in every direction but can sometimes line up neatly like disciplined soldiers? Well, that straighten up act is called polarization. Imagine light as a jumping rope being shaken up and down and sideways all at once. That's natural light vibrating in all directions perpendicular to its travel. Now, if we somehow restrict those wobbles to just one direction, that's polarized light. But here's a twist. Only transverse waves, where vibrations happen at right angles to the travel direction, behave this way. Longitudinal waves, like sound, which push and pull in the direction they travel, can't polarize. The famous experiment by Malus back in the day showed us this beautifully. He noticed that when natural light passed through a polarizer and then another filter that could be rotated, the intensity went up and down like a light dimmer. This wavy dance of light confirmed once and for all that light is transverse, vibrating side to side, not back and forth like a crowd doing the wave at a stadium. So, in a nutshell, polarization is light deciding to vibrate in just one direction perpendicular to its path, proving it's a transverse wave superstar. Now, let's get a bit more precise with our light terminology. It's like learning the difference between a jab and a cross in boxing but for light. The plane of vibration is the actual direction in which the electric field wobbles, the back and forth plane of the shaking, if you will. On the other hand, the plane of polarization is a bit sly. It's defined as the plane perpendicular to those vibrations, essentially where there is no electric field oscillation happening. Think of it like a dance floor. If the dancers move north-south, the dance floor plane, or plane of polarization, extends east-west where no dancers go. Polarizing devices act like bouncers at a club, only letting vibrations that match their preferred direction inside and blocking the rest. This is how we get plane polarized light, where the electric vector's direction sets the dress code for a loud vibration orientation. So when we talk about the direction of the electric vector, we are referring to the orientation of this disciplined, one-way vibrating light. Here's a fun fact. When unpolarized light, a jumbled crowd of vibrations, hits a smooth surface like glass or water at just the right angle, the reflected light comes back fully organized, vibrating in just one plane. That special angle is Brewster's angle, named after Sir David Brewster, who figured this out. It's the angle where the reflected and refracted rays are perfectly perpendicular. Imagine them making a perfect L shape. Mathematically, Brewster's angle is neat and tidy. The tangent of this angle equals the refractive index of the material the light is hitting. If you say it aloud, it sounds like this: the tangent of the Brewster angle equals the refractive index. So, at this magic angle, all the reflected light becomes plane polarized, showing us polarization is no accident but follows precise laws. Let's unravel Brewster's law step by step, like peeling an onion, except no tears here. We start with the fact that at Brewster's angle, the reflected and refracted rays are at right angles, which means the sum of the incident angle and the refracted angle equals 90 degrees. That is, incident angle plus refracted angle equals 90 degrees, so the refracted angle equals 90 degrees minus the incident angle. Next, Snell's law tells us that the ratio of the sine of the incident angle to the sine of the refracted angle is equal to the refractive index. Since the refracted angle is 90 degrees minus the incident angle, sine of that is cosine of the incident angle. So, the refractive index equals sine of incident angle divided by cosine of incident angle, which is simply tangent of the incident angle. Voila! We arrive at Brewster's law, where the tangent of the Brewster angle equals the refractive index. This beautiful relationship assumes a clean, transparent interface without absorption messing things up, a perfect example of physics' elegant harmony. Now, Let's explore a magical crystal trick called double refraction, famously performed by calcite crystals. Imagine shining a flashlight through a special crystal and suddenly seeing not one but two beams of light coming out, each with its own unique vibration direction. This splitting happens because calcite is anisotropic. It treats light differently depending on which way it oscillates inside. One beam, called the ordinary ray, behaves by following Snell's law, while the other, the extraordinary ray, marches to its own beat, ignoring Snell's law's usual rules. Each ray is plane polarized with their polarization directions at right angles to each other. The reason? They sip through the crystal at different speeds due to differing refractive indices depending on vibration direction, like runners on separate tracks. This neat phenomenon shows how crystal structures can influence light's behavior in fascinating ways. Have you ever worn those cool polarized sunglasses that magically cut glare and make colors pop? That's thanks to Polaroids, sheets made of long-chain molecules all lined up neatly in one direction, like soldiers standing in formation. These molecules absorb any electric field vibrations that try to shake them in the same direction as their alignment, but happily let through vibrations vibrating perpendicular to them. So, light passing through a Polaroid emerges plane polarized. These handy sheets aren't just for sunglasses, they're vital in LCD screens, optical instruments, and even stress analysis to reduce glare and reveal hidden patterns. But here's a funny twist. If you stack two Polaroids so their alignments are at right angles, guess what? All the light gets blocked. It's like two bouncers both denying entry to everyone, resulting in total darkness. This simple trick is a powerful way to control light in technology and science. Alright, time for a cool law you'll remember, Malus's law. When plane polarized light passes through another Polaroid called the analyzer, and you rotate that analyzer, the amount of light that sneaks through changes. The law tells us that the transmitted intensity equals the original intensity multiplied by the cosine squared of the angle between the light's vibration direction and the analyzer's axis. In other words, intensity equals I0 times cosine squared theta, where I0 is the initial intensity and theta is the angle of rotation. When the analyzer is perfectly aligned, meaning theta equals 0 degrees, maximum light passes through. Rotate it to 90 degrees and the transmission drops to 0, complete darkness. This nifty relationship proves light's vector nature and supports its wave model beautifully. It's like the light saying, I'm a team player, I obey your rotations. Let's do a quick example to apply Brewster's law. Suppose we have a glass surface with a refractive index of 1.5 and we want to find the Brewster angle, the angle at which reflected light is completely polarized. Brewster's law tells us the tangent of the Brewster angle equals the refractive index. So, tangent of the Brewster angle equals 1.5. To find the angle, we take the inverse tangent or arctangent of 1.5, which gives approximately 56.3 degrees. This means if light hits the glass surface at about 56.3 degrees, the reflected light will be fully plane polarized. A neat trick to remember next time you're dealing with reflections. To wrap up, remember these key points about polarization. Only transverse waves like light can be polarized because their vibrations are perpendicular to travel direction. Brewster's law connects the Brewster angle's tangent to the refractive index, helping us find just the right angle for full polarization on reflection. Malus's law tells how light intensity changes with the angle of a second polarizer, confirming light's vector and wave nature. And practically, Polaroids and special crystals polarize light either through selective absorption or double refraction. All these phenomena beautifully prove the vector and transverse attributes of electromagnetic waves. That's it for today's concept on polarization. Physics is fun when you can laugh and learn. See you in the next session.